Finally, also for the paper, a stable algorithm computing high-order 3D Zernike moments and shape reconstruction. This is my name, An-Wen. Let's talk about the abstract for our paper. 3D Zernike moment are used as the 3D object shape descriptor. In this paper, we introduce a series of stable algorithms for calculating high-order the 3D Zernike moments, a kind of a recurrence formula among 3D Zernike radial polynomials are presented. The voxel-based algorithm is hereby developed. The proposed method provides an accurate reconstruction image. When our algorithms are applied to the 3D object, Einstein goes with 100 times 100 times 100 voxels. The error rate for the shape construction attains its value 0.0000012 and 0 for computing all moments up to order 350 and 390 respectively. This is our theorem A. Theorem A is computing the normalized associated agenda polynomial. It can be computed in a recurrence way as follows. First one, you compute this guy, and you can use these 2 and 3 relation for the. You can use this formula and this guy. You compute the PLL and PLM ones. So the constant defined as follows. So it should be noticed that the normalized association lambda polynomial is given as the product of the constant KLM and the association agenda polynomial, where the KLM is this guy. So we talked about recurrency for the 3D Zernike polynomial. The polynomial Zernike polynomial VNLM is actually the product of the radial part with the sphere harmonic. The sphere harmonic can be computed as the product of the normalized associated agenda polynomial with its exponential function. So the radial polynomial is actually can be expressed in terms of Jacobi polynomial as follows. So we can prove the theorem B, which gives an algorithm to compute the radial polynomial. So the crucial thing is to compute those coefficients. The coefficient is given as follows. So for the application of this recurrency formula, you need the following initial condition. So the initial condition is the R and N of R is equal to R power M, and the radial polynomial Rn n minus 2 of R is equal to C. So how to compute the whole 3D Zernike moment? So suppose the while 3D image is within the cube, which consists of n power 3 voxels. Each voxel denoted by these things. So he has a center. We use this formula to compute, to approximate the 3D Zernike moments. So this guy, a radial polynomial, can be computed as given in theorem B, and this guy, the normalized associativity, the gender polynomial can be computed as given in theorem A. So in the next for loop, you can compute the whole thing. So we try our algorithm to different 3D object. So for example, we can apply to the Einstein box and the line. This box has this box 3D object have 100 times 100 times 100 voxels. So and after computing this moment, you can reconstruct the image from the computing moment. So this is the error rate for those 3D image. So you see, actually, probably near 300, we get almost zero error rate. So after submitting this paper, we apply our algorithm to the 3D object depth of 200 times 200 times 200. We can show your audience the construction as this video. This a moment compute at maximum order 50. A moment at maximum order 100. And up to maximum order 200. And moment up to maximum order 300. And finally, we compute up to maximum order 450. So you got zero error rate for this size image. Thank you for your watching.